in this segment, we'll consider another comparison sorting algorithm, which is also quadratic time, selection sort. Now, selection sort appears very similar to bubble sort, but it does not make nearly as many swaps as bubble sort does. So selection sort finds the minimum or the maximum value and puts it at the smallest or the greatest unsorted index, respectively. So if our original list is all in gray, selection sort will scan the entire list for the minimum value. In this case, it's 1. And it will put 1 at the smallest available index in the vector, which is at the position 0. And you'll notice here that we have 1 in position 0, and 1 is represented in red is representing the sorted portion of the list, and then we still have the entire unsorted portion of the list in gray. So that's after first iteration or first pass. And then on the next pass, we would scan the gray segment, the unsorted integers, for the smallest value. That would be 3, and we'd basically put 3 in the smallest available index, which is 1, and it turns out we don't actually have to do anything because 3 was already there. Okay, let's see what this algorithm looks like now. So selection sort, it is going to go through the list from left to right, and it will make the swap between the lowest available index and the minimum value. So we're saying let I be the smallest unsorted index, and we're going to let J traverse the list from left to right. Okay, so we start off with the smallest available index is just going to be 0, and the entire list is unsorted. So we set the index for the minimum value equal to I. We're assuming that that is the minimum value. And now we start scanning in the inner for loop. We start scanning the array or list from left to right in order to find the minimum. So here we have J equal to 1, and we're going to scan from left to right. So we're going to be comparing the value 3 at position J with I. Since the value 3 is less than the value 7, we are going to update the minimum to be 1. So the index to the minimum value is going to be pointing at 3. Then we advance J. We compare 8 with 3, no change. 6 with 3, no change. 5 with 3, no change. Finally, when we compare 1 with 3, you'll notice that 1 is less than 3, so 1 is at position 5. So we update the minimum index to be 5. And finally, after we break out of the inner for loop indexed by J, we perform this only swap, and that swap is going to be swapping the value at the smallest position, in this case I is equal to 0, with where we found the minimum unsorted value, which was 1. And you'll notice we swap 1 and 7. Okay, so that's the first pass, and you'll notice that we still did all the comparisons as we did in bubble sort, but we only do one swap. So now let's consider what happens on the next iteration. So we start, and now I is equal to 1, so I is pointing to where 3 is, and J is equal to 2, so J is pointing to 8. We compare them, and when we do this, the minimum, we're assuming the minimum is at position where I is, which is at position 1. We compare 3 with 8, no change to the minimum. 3 with 6, no change to the minimum. 3 with 5, no change to the minimum index, and 3 with 7, no change to the minimum index. And then we do the swap between 3 and itself. It's not a meaningful swap, and we have 3 in the second largest position at index 1, and we keep on doing this. And you'll notice that for each iteration, the red portion of the array, so that's the sorted portion, is increasing, and the unsorted portion is decreasing. And we can see that on each iteration we're taking out the minimum value and putting it into the sorted segment of the list. So in terms of runtime analysis, selection sort really is not that much better than bubble sort at all asymptotically, because you still have to scan the entire list every single time. That inner for loop just scans the remaining list in order to find the minimum remaining. And granted that this inner sum, you'll notice that the inner sum being indexed by j is getting smaller, but so you're looking at a smaller sublist because the unsorted gray list is getting smaller, but it's still going to be a quadratic time algorithm even when it's already sorted, but even when it's reverse sorted, so when it's sorted in descending order, you're still going to have a quadratic algorithm. The only benefit that we really get with selection sort over bubble sort is that we only make one swap, and this is more of a practical benefit. It's not really an asymptotic benefit at the least. And one helpful exercise is to think about how you would do this analysis more formally. So if I wanted to consider how I would do the analysis of selection sort, so one practice that we can do is we can think of T of n, and I can think, okay, well, my outer for loop is going to go from I equal to 0 to n minus 2, because we have to do less than n, where n is equal to my list size. And then we do some constant amount of work to just do the swaps and update the minimum initially, and then inside here, so that's constant to do the swap and update the minimum, we would be doing our nested loop. But you'll notice that this loop is going from j equal to I plus 1 to n minus 1, and it's just doing the constant work in here. So I think that's sufficient right now. So now we can just see how we can simplify this and how we can actually get this into a closed form. So I'm going to change to green. So we can actually pull these sums. So here we're just going to have the first sum. If I'm applying the linearity to the summation, I can just have C1 times n minus 1. So that's this one. And now I'm going to handle the nested summation. So I'm going to have I going from 0 to n minus 2 times the summation as j going from I plus 1 to n minus 1 of a constant amount of work. So now I'm going to do a little bit of work now just to make the summation a little bit easier to deal with. So now inside here, j is going from I plus 1 to n minus 1. So we can simplify this. The way that we can simplify this is we can observe that the inner summation is not actually doing anything with j, so we can translate this to be n minus I times C2, and this inner summation here is going from, we're going to just do a change of indices. This is going to be 1 to n minus 1 right there. So now it may seem complicated to deal with this summation n minus I times C2, but we can simplify this further, and the way that we can do this is if we start plugging in values, we can see that we're just going to be adding together C2 times n minus 1 plus n minus 2 plus all the way to 1. And when we observe that, we can just change that. So we can rewrite the summation index by, say, k. It's going to be the summation as k goes from 1 to n minus 1 of k times C2. And I'm going to pull out the C2 here. And you'll notice that this is the arithmetic series, so now we know we can apply the asymptotic bound, and we just get n squared from that. So this is how we can see it more carefully, because the inner loop is going to be, that inner loop indexed by j is going to be changing each time, but we'll still get a quadratic runtime. The next thing that we want to consider is the stability. Is the selection sort stable? And our claim is no. And the way that we can show that a sorting algorithm is not stable is to give a list for which we would show such instability. So let's consider the list 3, 3, 1, and you want to find the smallest such list. And I'm going to change the color of the second 3 to be green. So now let's see what happens when we apply selection sort. So when we apply selection sort, we're going to have I here, which is the smallest index, and we're going to start comparing I and j. So we wouldn't update the minimum, so we start off with the minimum set to 0. And we would compare 3 and 3, it's not less than, so then we'd move over to the j equal 2. And when we see j is equal to 2, we know that 1 is less than 3, so we would update the minimum to be 2. And so then what we would do is we would do this swap of whatever is in positions I, which is 0, and my list minimum, which is 2. So we're going to perform that swap now. And when we do this swap, we're going to get 1, 3, and our green 3 stays in the center. So you'll notice we've just reversed the order of the 3's, and the next pass would not make any changing. So this is why it's unstable, because the order of the 3's in the original list is not preserved. And that is because in the original list we had the blue 3 before the green 3, and now we have the blue 3 after the green 3. Okay, let's consider the loop invariant for a selection sort now. So what is the predicate that is true after the kth iteration? So here we can again think of this in terms of the gray and the red segments of the array, where the gray is the unsorted segment and the red is the growing sorted segment. So the gray unsorted section is shrinking and the red sorted section is increasing. So it's saying that all elements at index k less than k are sorted, and all of those elements at indices greater than or equal to k are greater than the sorted portion, but they're not necessarily sorted within themselves. So the first statement, this is saying that the red segment is sorted, and this is just saying that everything in the gray unsorted area is at least as big as the largest element in the sorted portion, the red portion of the array. And let's see how we can see that, so we can have less that if we actually had equal elements. If they were all distinct, this would be fine. But if we have equal elements, so you can see that after the first pass, we have the minimum value of the unsorted array in the smallest index. So we have the k would be equal to 1. All the values at the indices less than 1, so that would be 0, are sorted. So there's nothing greater than that, so that's sorted. And then you'll notice that everything that is unsorted, everything that is still in the gray portion of the list, has a value greater than the largest value, which is in red, which is 1, because we just moved the minimum. And you'll notice even after the second pass, we move 3 to the sorted section, and you'll notice when we compare the first element in the sorted section and the second element in the sorted section, so 1 and 3, they are sorted relative to each other. And then in the gray segment of the unsorted portion of the list, everything in the unsorted portion is greater than the largest element, 3, in the sorted section. So that's all that the loop invariants are saying, is that after each iteration you will be increasing the sorted section in red to be the sorted values, increasing sorted values, and that anything that is unsorted has to be at least as big as the largest sorted element in red.